Yeah, hello and welcome to our next lesson of the PML school, where we want to teach you how to write and understand models in Phoenix modeling language. My name is Bernd Wendt and I'm going to talk today about a two-compartmental model with repeated dosing. Two-compartment, you might think this is a rather simple task. Why shall we bother with this in this session? And in fact, I have to agree, it is a simple task since this model can be completely set up by the built-in options of the Phoenix model object. But as we stated earlier in one of the first sessions of the PML school, we have selected the exercises on the basis of support questions that are related to these exercises. And this supposedly simple model has led to one of the highest frequencies of questions in support. So we can only guess that many users of the classic Win-on-Lin PK model libraries, the Win-on-Lin 5 version type of libraries, might have difficulties with some of the challenges of these exercises. So, for example, the repeated dosing schedule or fitting both pharmacokinetic as well as pharmacodynamic data. And that is why we think that it will be interesting to many users to go through this rather simple model in more detail. I hope it can lead to a very good Q&A session at the end, which we will do as usually. And you can use the Q&A widget on the right-hand side of the console at any point in time during this webinar, and I will cover most of the questions hopefully after the webinar in live. But as we've outlined in one of the messages that we sent out, we will now start and publish all the questions with corresponding answers in an anonymized form on our forum, the usual place where we exchange the materials, the link to the recording, and so forth. So let's move on. What is the objective of this exercise? First, we want to fit multiple dose PK data. And once we have fitted this, we will freeze the PK parameters and then fit a dynamic model to the response time data. Overall, we want to find estimates for quite a few parameters. For example, for PK, for a two-compartmental model, we have the two volumes, two clearances. Since it's extravascular data, we have the absorption rate constant. And in addition to that, we will also estimate a lag time between the dose point and the first measured concentration. For the PD part, we've got two parameters, EC50, this is the half maximal effective concentration, and Emax, the maximum drug-induced effect. So that's the task, that's the objective. What do we have? Typically, we have one subject, so we want to keep it simple with individual modeling, which this subject received a single oral dose at 400 mg on day 1. Then there was a pause, and on day 5, the same subject started to receive an oral dose of 400 milligrams 3 times daily for the continuation of 5 days. And on the last day, day 9, the subject only received a single morning dose. During the study, plasma samples were collected at various times until 72 hours after the last dose. The drug effects were measured prior to each blood sampling. So this is the protocol. Now, if we come to the data itself, this is the data in one plot. So I've overlaid the PK data, the concentrations with black dots and without a line, with the PD data, the responses in blue. And you see from a first view, first look, that the PK and PD profile have the same kind, the rise and the decline are happening at the same time, so we can assume instantaneous equilibrium between the PK and PD. So that is why for this exercise we don't need to consider any more complex PK/PD model like a PK/PD link model or something like that. So we will keep it at a very simple level. how do we set this up in Phoenix, in the Phoenix model object? That's rather straightforward if you're familiar with the options, the built-in options that is shown here on the top. Maybe I'll just take one of the laser pointer. So the first thing we typically do is check off the population box because we are doing individual modeling. The next one is the type of model. Here we choose PK because we just want to fit the PK data of the data set first, followed by a PKPD fitting. We go just below that. There are 3 blocks: parameterization, absorption, and number of compartments. For the parameterization, we keep the default, which is clearance, and we uncheck the box closed form, which is typically by default, I guess it's on. So we want to deal with differential equation, not with integrated forms. So that's why we check it off. For the absorption, we have to switch from intravascular to extravascular. We have an extravascular dose. And here's an optional checkbox, T-lag, which deals with the lag time, which we also want to include in our model. So we just check it on here. Then we need to we adjust the number of compartments. In this case, it's 2. So we change it to 2. So that's, I guess, is all. I mean, we have here in the bottom the residual or error model, which we leave as default. We usually start with the most simple model, which is an additive residual error model, and standard deviation on the residual error we keep at 1. This is a typical starting point, so we keep it by the default. And that's mainly it from here. And you see already the model text. We are coming to this in more detail on one of the later slides. Once we've fitted the PK model, we will then switch to the PKPD model, and that is shown down here. There are just two tiny steps that we need to do. For the type, we switch from PK to PK Emax, and because we want to freeze the PK parameters, so we don't want to let them also be fitted during this exercise. We just switch on this box, freeze PK. Since we switched to PK Emax, we have another block here for the Emax model, where you can switch to baseline, inhibitory, or sigmoid. And here's the formula, a typical Hill equation. So this is something where we don't need to adjust anything. We just keep with a simple Emax model. We also keep a very simple residual error model for the effects, so it's an additive. So this is everything. So it's no further steps. This is how the model is set up. So it's very simple, very straightforward, but it might be very useful to know. So there's typically some, and we have seen that in one of the previous sessions, there are some questions about the residual error model. This is also what we've published on the forum as responses to the residual error model. That is, you can change from additive to other models. We come to that in the demo session. Typically, you would change it to multiplicative to give it a different weighting on the individual concentration ranges, the residuals on the concentration range. But let's do that while we are in the demo round, because then I can show you a little bit more around that. So these are all the built-in options, and this is sufficient to set up all the options for this model, for a two-compartment PKPD model. So let's move on. Look at the graphical model. This is just a different representation. I didn't change anything within the graphical model builder, which is optional, which you could do, but for this exercise, we actually don't need it. Let's just describe what you see here. So you see here this upper triangle with a name AA. This is the absorption compartment. It's like the depot for the dose, for the bolus dose that is being applied here. And you see a one-directional flow to the central compartment, and the flow is governed by a absorption rate constant, Ka. Then for the absorption compartment, we also have another parameter, the T lag, which is implicitly linked with this part, and we come to that when we go to the textual model. So from the central compartment, we've got the volume and the drug amounts. We have a bidirectional flow to a peripheral compartment with the concentration C2 and the volume V2. And we have another flow, a one-directional flow to the elimination compartment, and that is governed by the clearance. And we have also this intercompartmental distribution with another clearance, Cl2. So this is a graphical description of the PK part of the model. When we switch over to PK Emax, just two blocks are added to the graphical model. There is an effect block, and the effect block is linked to the central compartment through the concentration. So the effect is calculated by the predicted concentration from the central compartment and is estimated with EC50 and Emax. The effect is measured, as we have data points for that. It's the observed effects that are linked with the effector block. So this explains the graphical model. When we come to the textual model, maybe let's have a short look at the model equations. And what you might have already seen in one of the previous sessions, when we use differential equations in Phoenix model, we will calculate the change of amounts rather than concentrations. And this is just given here for a very simple case, for the most simple case, IV bolus one compartmental model. So we can say that the change of concentration by time multiplied by the volume equals the change of the amount by time, and that is the equation minus clearance times C. So the amount gets smaller over time. When we switch from one compartment to a two compartment, there's just another expression added to this. So this is the former one, the elimination through the clearance, systemic clearance, and then we've got an intercompartmental clearance, that is the CLD value times the concentration of the central compartment minus the concentration in the peripheral compartment. Now for an extravascular model, we need extravascular input, and that is in the form of the Ka, the absorption rate constant, times the dose amount. And that makes up the whole equation. This is actually what we want to see. If we want to calculate the amount in the central compartment, this is the equation that we need, the differential equations that we need to use there. For the PD model, we are using really just a simple Emax model. It is a Higgs-Hill equation, E equals Emax times C divided by EC50 plus C. So these are the equations that you typically get from a reference, a book like the one shown below in Gabrielsson and Weiner, where all these equations are listed and also how it got derived. So this is a typical starting point. And you see when you go to the textual model, how easy it is to transfer this information to the PML code. And from there, you can try changes and adaptations according to better adapt your specific scenario. So if we go to the textual code, it might be a little bit small to read, but hopefully you get the idea. This is the typical structure of a PML code. It comes with three parts: the structural model section, error model section, and parameter section. For the structural model sections, this is actually the part where you enter the differential equation, and that has typically the form of the deriv statement, which gives you a value, for example, AA, that equals is this form minus Ka times AA. So the absorption rate constant times the dose amount. Or when you look at the main differential equation here at the center, this actually is directly adapted from the reference, if you will, from the book that you just enter here. And this is similar to that, I mean, the differential equation to calculate the changes of amounts in the peripheral compartment. For the dose point, this is just giving you an information that it's an extravascular dose, AA, plus an option that we use, the T-lag option, where you have a parameter that needs to be estimated called T-lag. There are several other options of the dose point function that we get to know through the further exercises that we will handle, that we will cover in the next sessions. Followed by the dose point are some general equations, and this is just converting the drug amounts to drug concentrations by dividing through the volume. And then we've got the expression for the effect, and the effect you just enter the Hill equation, like you saw on the previous slide. For the error model, this is, as I said, the most simple model. The first statement error calls the error variable called EEPS and sets the initial estimate for the standard deviation of the residual error model to 1. And here is here's observed statement for the error model. So everything you have measured, these are the EOPS data, the observed effect data, is a sum of the predicted effect from the model plus the residual error. That's how we set up the error model in PML code. Now for the last section, the parameter section, this might be a little bit confusing because it shows a lot of statements here, and it typically comes first the structural parameters, ST-PARM, which in this case is very simple. It's just an assignment of, it's just Ka, for example, equals TVKa, which is just a different naming. But this is very useful, and it originates from population modeling, which we are not actually doing here, but because you can switch to population modeling by a simple checkbox, you've seen that in the built-in options, it is left inside the PML code. It's very useful to get to know it once you are at the stage to enter into population modeling. You are already familiar with the syntax here. So what the syntax says in the structural parameter is that you have a structural parameter like Ka. And that is, here you can combine a fixed effect, a typical value. This means this is the best estimate for a population, or in this case for this individual, for this subject, and combined with a random effect. If you have a population, there might be some between subject variables that you can cover or can explain through these random effects. That's why you would have this standard the structure PARM statement in the PML code. We could, leave this out for our exercises, but I think it's a good exercise and good practice to keep them in order to keep up with the same syntax, with the same structure. So in this case, we just assign different names to the structure parameters, and now we come to the fixed effect, which are the best estimates or the estimates for the structural parameter. And here you see the syntax TVKa. This is just taken from this first statement. And it's frozen because this is a PKPD part where we wanted to fix this effect to be just this number, nothing else, not to be estimated. So we put a freeze option into this statement. And then it's assigned to a vector, a C statement, C function, if you will. And this C function expects 3 values, comma separated, with the first value is the lower boundary, the second one is this initial estimate, and the third one is the upper boundary. For all these parameters, we haven't specified any boundaries, and that's okay. So the program will not consider any boundaries. For the PKPD part, we only let these 2 PD parameters be estimated, EC50 and Emax, and here we have the initial estimates set to 2 and 100. So that's the actual textual code. Before we start with the demo, we need some initial estimates typically. So, and what we typically do here is run an NCA analysis. So we get the clearance from the NCA by the estimation from the NCA, CLF ops. For the central volume, we just get an initial estimate by the dose divided by Cmax. For the peripheral compartment, we take VZ, VF ops from the NCA. Ka should vary around 1, so we start with a value of 1. And for T-lag, we just look at the data and see the first measurable concentration after the dose, which in this case would be 0.5 hours. Okay, what are we doing through the demo? So the modeling strategy is we are running an NCA to get the initial estimates. We are only using the built-in options to set up the Phoenix model. We will fit the PK data first. We will fix the PK parameters and then fit the pharmacodynamic data. And that's it. I guess we are now ready for the demo. Let's share Phoenix application. Okay, so here we are. This is our model. It's PK11. This is the number of the exercise in the Gabrielsson and Weiner book. So you can look it up there for any more details. I've put in already lots of worksheets. Typically, you can start with this a big data sheet where you have the times, the type, PK and PD data. PKPD data, the plasma concentration and the responses, but I've split it up into the PD data here and the PK data here. Also, I've already set up the dosing table for the different multiple doses. For the workflow, we usually start with an exploratory plot. So we look at this. This is what you've seen already in the slides. It shows the same timing of the profile between the concentration and the effect. That's good. You can also plot the PK/PD data, so the response versus concentration, to get some initial estimates for your PD model, like the EC50, for example. When you look at it, it's roughly between 0 and 100 in response, so the middle might be somewhere in 50. When you go down here, it's maybe 1 or 2 milligrams per liter for the EC50, and the maximum effect should be somewhere around 100. So this plot gives you some initial estimates for the PD model. For the NCA analysis, we need single profiles. So what I did is I used the data wizard object to just take all data points before the second dose, so before 96 hours. And that is what you get. So this is a single profile, and you run it by NCA. And then you get some values out of here. These are the final parameters from NCA. For example, Cmax is roughly 20, say 20, and we have a dose of 400. So that means that the volume of the central compartment, which is dose divided by Cmax, is around 20. Then we've got these two parameters, the volume and the clearance that we take from here as well. So with that, we can start building the model. We take the PK data and send it to a Phoenix model object. Okay. Before we look at the main mappings panel, we go to the individual built-in options, so where we uncheck the population box. PK is correct. So this is a PK model. Clearance is okay. We said we just want to uncheck the closed form. We switch to extravascular absorption, and we want to have T-lag included. And then we also want to have 2 compartments. You see, while I'm clicking all these options, the PML code appears here on the right-hand side, so you can easily follow what are the individual terms that are changing throughout these built-in options. As I said, we will stick with a simple additive model for the residual error. And now we can go up into the main panel and do the mapping. So time is already mapped. Cp, the plasma concentration, is our observed concentration. And this is how the model looks like. This is what I described on the slide. So I don't need to go into detail here. For the dosing, I have already prepared the dosing table, so I just drag it over here and adjust time to time, and the amount is AA. That's it. So we should now be ready to enter the initial estimates. That takes some time. So we have here the initial estimates. Time goes until 250, so let's adjust the time. And you see how the individual doses appear on the initial estimates tab. Typical value of Ka, we said we leave it by 1. The central volume, we said it was 20. And the peripheral was 80. The clearance was 5. And the same for the intercompartmental clearance. And for T-lag, we said it was a value of 0.5. Okay, you see roughly the fit. This is, I would say, good enough. So we just say, okay, go ahead and run the model. Okay. So here's our model. Here's a fit of observed predicted versus time. Let me pop this out and adjust with a Y to the logarithmic scale and maybe make the graph a little bit wider. It's not a perfect fit, but it fits our purposes, so it's not too bad. What you see, it's a pretty sparse calculation of predicted concentrations, and that's typically for the NLME. So what we usually do in order to get a better fit, we can choose the run options here to add another table to get a more finer predicted concentration time curve. So we just add a table here, and we say we want to have a sequence statement which starts at 0 hours until 250 hours, and let's say with a time interval of 0.1 hours. And when we observe, we want to get the observed value, and all the predictions that we want to get is C, the predicted concentration. So if we run this once again, you will get a table where you have the time, the observed concentration, and the predicted concentration. And this we can easily send to a plot object where we have C time on X, C ops on Y, and C on Y. We already adjust the Y scale to logarithmic. We want the graphs, the curve for the observations to not show lines, just markers. Maybe give them a red marker border color. For the predicted concentration, we don't want to show markers, and we let the appearance stick with it, with a black line, and that's what we get. This is the actual, more finer curve with the this is something where we can go to the plot layout and make it a little bit wider. So we see that it's really nicely fits here, these peaks. There's a slight deviation, you know, maybe we need a third compartment here because it's under predicting. But this is of minor importance. It's just a very nice fit with a multiple dose profile. So we are happy with the outcome here. We can call this is our PK model. And this is our PK observed, predicted versus time. Okay. Now, what we typically do is we copy the PK model and paste it back to the workflow. And this we will just call PKPD model. And as I said, there's not a lot you need to change in order to transform this PK model to a PKPD model. We say PK changes to PK Emax, and we freeze PK, and that's it. So you have the Emax model now, and the equation here, the Hill equation, and the residual error model of the effect. Obviously, we need to change the input data, the main data, which will become the PKPD data actually. So we need to map time to time and the response to the observed effect EOPS. Dosing stays the same. We got frozen PK. What we need to do is actually, from the fixed effects, we need to accept all fixed and random effects from the previous run. So these are then taken over as initial estimates, and they are frozen. Okay, and then next step is we need to get to some initial estimates. And you see here, it's already switched to E versus time. Those parameters we don't want to touch, they are frozen, they are fixed. But EC50 and Emax we need to adjust. And what we stated when we looked at the PKPD plot was that Emax was around 100, and EC50 was around 1. And you see, it's not too close, but close enough to get a good, nice fit out of this. So we can just stick to what it is and run the model. But before doing that, we need to change something here in the additional table. We also want to have a finer plot on the from the PKPD model. We don't have COPS in our data, so we need to change it to report on EOPS. And for the variables that we want to, the predicted concentration and the predicted effect, we want to also have in our table output. That's all what you need to set. Everything else stood the same, so we just give it a go and execute the model. Here we are. So this is obviously not a very nice plot, so we just need to get our table, our predicted. This is our times, the observed effect, and the predicted concentration is a predicted effect. We take that and send it to a plotting object, XY plot, and say time we put on the x-axis, EOPS and E on the y-axis, and C on a different axis, y2. What is missing is the observed concentration, so we just need to add another graph. This is done here on the plot. We just add another graph where we can just bring over the PK data, where we've got time on X and CP, the plasma concentration, on Y2. Now we need to adjust a few things. EOPS, we don't want to show lines, and maybe a blue marker color with some blue dots. Come on. And for the predicted effects, we just show the lines with the blue color. For the predicted concentrations, you might want to show it in red. For the observed concentrations, we don't want to show lines, and we take red markers. For the concentration, we might want to look at the logarithmic scale, so we turn Y2 to log scale and then execute. That's what you get. We need to make the plot a little bit wider again. And here you see the outcome of the model with the overlay of the concentration and the response. So this is how you can simply do PKPD modeling with multiple doses. Maybe one hint with regards to doses, we can, you see when you look at the doses, there are quite a number of doses that you have to specify, and this is just for a single person. Imagine you have a whole population study, there are lots of records that you need to take care of, and therefore there's a shortcut to this, and I will just show you a shortcut of this version. So what I did was I created another data set which includes the responses together with the dose information, and here we only have 2 records for the dose information. The initial dose on day 1 at the time point 0, the amount 400 mg, and then the next phase started after 96 hours, also with the amount of 400, and after this 96 hours we had 12 additional doses. That's why I've created here the additional column, which just gives the number of additional doses. And that's what we can use in our PKPD model as an input options. Let me copy this PKPD model and paste it back to the workflow. And then we just eliminate the dose section and replace the main PK data with PD data with doses. And here on the bottom, you just need to go to the input options. There are further other input options that we come across in subsequent sessions. This is additional doses. And here we just need to enter an additional dose, and it asks for the delta time, which is a constant in this case. And it is 3 times daily, so it's 8 hours delta time. The dose point is AA, it's an extravascular dose. And the amount we will give is a column called AMT. This is this column here. Okay, that's what it is, and it already accepted the additional column, which gives information about how many additional doses were given. And if you go to the initial estimates tab, you will see that it recognizes the same number of doses, and it can deal with it, repeated dosing this way. I think this was just a good opportunity to show you this function as well. But this is all from this PKPD model, from the software demo. Let me go back to the slides. So this is an end result. So we have fitted the data, the PK in red and the PD in blue, which gives a nice model, and with the number of, with quite a few number of parameters that we've estimated with very good CV%, so very good estimates. And to summarize, we simultaneously fit, no, this is a wrong slide. We just built a model. We had to get some initial estimates. We fit the model to the data, and I hope you had a chance to learn how to code, how to transfer this built-in library model into the code. We looked over that, and with that, I just want to end this session, and maybe we can go over to the Q&A. So let me go to Q&A. So we've got quite a few questions. So let me see. There's one question that asks, why is the PK frozen, the freeze PK checkbox checked? This is something. This is really up to you. This is optional. But what that is typically what you do in with PKPD modeling. You've seen we've got quite a number of parameters that the algorithm has to estimate, and if you have too many parameters, you might not find the best estimate from this, because it's a hyperdimensional surface, and to find the global minimum on such a surface is pretty difficult. So you want to deal with it in steps. And what is very common in PKPD modeling is to try to fit the PK data first. So you got a set of PK parameters that nicely fits the PK part of the data. And you then reduce the dimensionality of the problem that the engine has to solve by just freezing the PK parameter. And then just let the PD part fixed with a frozen set of PK data, and then you get some good estimates for the PD parameters. This is not necessarily the way you could go. If you are very if you have good estimates for both PK and PD data, you might not freeze PK data. This is your choice. So you can run PKPD estimation for both sets of parameters, PK and PD. But I'm just showing you these additional options, freeze PK, because it's really commonly used, and it's really gives you very good results. But it depends on your situation. You might not want to take it. The next question is, what is ELM-CPT? That's an elimination compartment. You know, this is something is like the absorption compartment. It's not really a compartment. It's just a way to visualize, you know, the model in descriptive ways. So you have a depot where you swallow the pill, for example, and that is your absorption compartment. Once it enters the system, the blood, I mean, you can measure it in your and you can get a concentration predicted for that. And the same with elimination. How it is going to eliminate it, we don't know. I mean, if it's a renal route or whatever. So it's just a description of what could happen and a simplification, and it just helps you to measure amounts, how they got changed from one compartment into the other. There's another question about the closed form and saturation form used in clearance. These are just optional things that you want to check. If you see some saturation in clearance, you want to check that on, and you will get a Michaelis-Menten kinetic term for derivation of clearance. And the closed form is just a different form of how you want to express how you want to calculate the change of the amounts over time. When there is an algebraic solution available for your model, then the closed form would be the solution to go. But here in our case, we stick to the differential equation because we want to use it throughout all the sessions where sometimes you don't have an algebraic form for a particular model. So we want to be as consistent as possible and choose just the differential equation form. There's one question: do we need to use ADDL for additional doses, or can we enter dose, time, and dose for each additional dose in the input file? Yes, this is optional. You don't need to do that. I just wanted to show you a simple trick. I mean, how you can maybe reduce your work in setting up dosing tables. If it's a really regular, a regular scheme like we have here, then maybe the ADDL option will save you time. But if you really want to use the explicit dosing table, you can do that as well. Either way works. As I showed you, it gives you the same information, the same results. It's just the way how you input the data is different. And okay, so next thing is how to set initial estimates of TVKA, TV, TV2 from NCA. I think I've shown you this. On one slide, it shows you what kind of values you should look up in the NCA analysis on the final parameters worksheet, what to do, and what are the things you have to enter into as initial estimates for your model. And this is, I mean, I can maybe show it to you. You can enter the oops, no, let's see. is it? You can enter the initial estimates here in this initial estimates tab. These are the values that are the initial estimates. And once you enter these here, you can copy them to the table. And when you want to check that you have the right initial estimates set, you go under the parameters tab, fixed effects, and here you see these are your initial estimates, how the program will use them. So this is a place where you can enter them as well, but it's better to have them right with the display right on the right-hand side, so you know these are the right set. This is the right set of initial estimates. Okay, let's go back. Yes, can you share the final Phoenix project file together with the slides on your server? What we can do is we can share the textual model part. This is an arrangement with the publisher of the book from where we got the material, and we will also make the slides available as well as the link to the recording of this session. How usually it is that you do not need to model an effect compartment. This is really up to the data that you have. Typically, yes. If this is also physiologically, I mean, if the effect is going to take place in a peripheral compartment, chances are that you need to have an effect compartment in your model. But I would make this up just on the exploratory analysis, right? You see that if there is a delay between the rise in the concentration and the rise in the effect, and then you can check whether effect compartment improves the model or not. Can you have one input worksheet with both dosing, PK, and PD data? Yes, you can. And this is something I've shown. I mean, the dosing part together with the PD data, but you can also have PK data there in that as well. I don't think, could you please repeat the method setup step for using ADDL function? This is a recorded webinar. I would suggest you just look it up on the recording, and you will see it's really a very simple steps that you can easily follow. Can you elaborate on the addition of the table? Does it provide more data points so that the fit improves, or is it just plotting the fit differently? It is predicted concentration from the model and with its final estimates. So it does not improve, it does not interfere with the fit at all. It just does the plotting in a better way. It gives you a finer curve so that you can see some subtle differences. You know, with the multiple dose, you want to have a more finer curve, and in order to follow the individual doses. Can you elaborate more about residual error option select on page number 5? The residual error model, we had a lot of discussion in the forum, and I would suggest we continue with the discussion on the forum, because it's a more complex topic where you can have a lot of options. I mean, maybe if this continues to be a big question for many people, we will maybe schedule a separate session to deal with residual error models. I need to think together with Chris Mehl about that. Maybe we'll have an extra session on those, because I see that this question comes up quite a number of times. Here comes another question. If I have urine volume and concentration data during multiple periods of time, is it useful to add the urine data into the PK model, and how? This is actually another exercise, another model, how to incorporate urine data, like urine volume and concentration data. Makes a lot of sense if you have the data, and it will obviously improve the fitting and gives you more confidence in your parameter estimates. We have already dealt with the closed form question. Wait a second. There's one question. How can we get the raw data for the PK analysis? I have the Gabrielsson book. Actually, we are working with the 5th edition of Gabrielsson book, and this comes with a USB stick, and all the Phoenix project files are contained on this stick, so you can just take the project file from this USB stick and and run it within Phoenix. That should be straightforward. If you have a previous version of the book, I guess you would have to enter the data manually. That's the only option that I can see. And how do we get secondary parameters? That's a very good question. Maybe this is one of the last questions. There's only one other question about bootstrapping. We can't deal with bootstrapping here because we don't have population data available. Okay, let me just this is maybe the final question. Or how do we get secondary parameters? That's actually a good idea. Let me stick with this PK model and show you how to get secondary parameters. I'll just make a copy of that in order to see. So this is, where does it come? Oh, yeah. Oh, wait a second. I wanted to copy this, paste this in here. So, secondary parameters you can enter under parameters and secondary, and where you can have the option to add some parameters, like you can go, for example, AUC, and then you need an expression how to calculate AUC, right, or AUC inf. If you want to learn about this, the best way is to, we've got a two-compartment clearance model extravascular. There's lots of definitions already for secondary parameters in the classic Winn and Lin library. So if we switch to set Winn and Lin model, you can say I had a two-compartment two-compartment extravascular. Is it two-compartment micro? And we choose clearance, and we replace this. So we just picked a library from the classic Winn and Lin library. When you now look under secondary parameters, you've got already defined parameters for many of those that you are familiar with. Take those as a starting point to get expressions for what you actually want to see in your model. But it's much the same way. If you want to have some secondary parameters, you can define them here. I guess with that, we are at the end. I want to thank everyone for their interest in attending this webinar series. Action items for me is that I will post the material on our forum, the slide deck, the textual model, and the recorded webinar. And please post some additional questions or comments on the forum, and we will make sure you will get an answer. For all the questions that we have seen here today during the live webinar, we will anonymize those and put them together with responses also to our forum. And I will follow up with an email to all the attendees after this webinar to summarize this information. So thanks everyone for your interest, and you may want to disconnect now. Thanks.